Next speaker for this afternoon. So we will be having Associate Professor Mario Lanza. So Professor Mario got his PhD degree in electronic engineering in 2010 at the Universitat Autonoma de Barcelona. He is currently an associate professor in material science and engineering. He has published over 140 research articles and has registered 4 patents. He is a distinguished lecturer of the Electron Devices Society, or IEEE EDS, and he has received multiple funding projects, one of which is a 1 million talent, and then an international awards. Ladies and gentlemen, Professor Mario Lanza.
Hello, everyone. My name is Mario Lanza. I am an associate professor at the King Abdullah University of Science and Technology. I would like to thank the organizers of the conference for inviting me to give this presentation. The title of my talk today is going to be Characterization of Neuromorphic Response using a Conductive Atomic Force Microscope. This is the outline that I will follow. And first, I would like to start by making a brief introduction about membristive artificial neural networks. As probably most of you know, artificial intelligence systems are going to be producing a lot of benefits for modern societies, especially in terms of economy, wellness, and national security. These systems are normally based on artificial neural networks, which are mathematical models that compute an amount of inputs and they associate one value at the output. In the output, we have several classes. Depending on these values at the input, they make one association or another. These values at the input can represent one image or one audio or one video or different types of that data sets. Most artificial neural networks are based on a building block called the perceptron, which basically consists on one group of synapses. These synapses, what they do is they multiply the value of each input by a number. And there is a sum of all these values. The resulting value after the sum is compared in a thresholding element. And then when this comparison gives a positive value, then the output is activated. There are different types of perceptrons with different activation factors. And this is something that somehow resembles roughly what it happens in a biological brain between the neurons and the synapses. So the main question here is how to implement with hardware this perceptron block. So the state-of-the-art commercial chips that are emulating artificial neural networks use transistors. And these transistors, you need several of them in order to emulate the functioning of one single synapse and also one single neuron. For example, the True North chip from IBM uses 6 transistors to emulate one synapse. These elements, even with that, they may not resemble the theoretical wanted technological requirements, which are the synapses need to exhibit multiple states, they need to exhibit a linear transition between them, and they need to be able to potentiate and to depress, which means to go upwards in these levels and also downwards. For the neurons, they need to have 2 states. One of them needs to be unstable, so that it needs to have a relaxation, and the transition needs to be highly nonlinear. A part of this common technological requirements for both of them is that they need to show a low power consumption, a high yield, low variability, high endurance, and high integration density, as I will mention later. So the point is that some scientists have started to use membristors. Only one membristor can emulate the electrical behaviors required for one electronic synapse and also for one electronic neuron, because the membristors can exhibit both threshold type resistive switching and non-volatile bipolar resistive switching, depending on the materials that we use to fabricate these membristors. The membristor is basically a metal insulator, metal junction, and when we apply an electrical stress, this is transmitted to the output after a certain time, which is something similar to what happened in one biological synapse or in one biological neuron. So here we observe one example on how to use membristors to fabricate one perceptron. This block with the synapses is basically a vector matrix multiplication, which can be done with one crossbar array of membristors. And this comparison that is done by the network, by the neuron, can be done using one membristor that exhibits threshold type resistive switching. Here we observe one example of one artificial neural network that contains 8 perceptrons. Each perceptron is one column and it contains 8 inputs. The input value is multiplied by the conductance of this synaptic membristor. Then all the values here are summed and they are transmitted to this neuron, which is what makes the comparison. The synapses in this example are made of membristors that have a tantalum, have new oxide palladium composition, and the neurons have platinum silver, silicon oxide doped with silver, silver platinum chemical composition. So basically, this is one example on how to fabricate a simple artificial neural network using an array of membristors. However, they still cannot resemble perfectly all these technological requirements that I have mentioned before. And therefore, investigations using new materials to fabricate these membristors are highly necessary. Before going to the fabrication of the membristors, let me dip in a little bit more into this integration density issue. So if we check the number of neurons and the number of synapses in a human brain, it is huge. We are talking about 100 billion neurons and 125 trillion synapses roughly. However, when we check the works that most of the studies that analyze membristive synapses and membristive neurons, we can observe that most of them employ high device size, which is not matching any integration density criteria. So what we are trying to do is to explore synaptic response at the nanoscale, which is what we do in our recent paper, which actually all this presentation is going to be focused on this paper. So one possibility that has been used in the past is to use a scanning tunneling microscope in order to explore nanosynaptic response at different locations of materials. This was done and some relaxation and some potentiation was successfully demonstrated. However, in this setup, there is a big problem, which is between the metallic tip, which serves as electrode, and the material and bottom electrode, there is a nano gap here, which doesn't meet the real conditions of devices. So what we are doing in my group is to use one conductive atomic force microscope instead the scanning tunneling microscope. Because in one conductive atomic force microscope, there is no nano gap between the tip and the sample. So the first that we do is the synthesis of the materials. We fabricate the graphene oxide. Well, our collaborators fabricated the graphene oxide at the University of Cambridge, the group led by Professor Andrea Ferrari. They produce these large and thin flakes of graphene oxide, and we deposit them as a film. The film has this outlook after it is deposited. It contains several flakes. It's a mesh, it's a film that contains several flakes with random orientations, and we observe some wrinkles, some faults, something that what we expected. The properties of the film are good. It is from a crystallographic point of view, it has a good structure as confirmed by the Raman shift. And also it is highly hydrophilic, which is something good in order to ensure a good conformal coating of the materials that we are gonna use. So this is the system that we use to spray coat the the material, the graphene oxide. It is a commercial system. We use some standard parameters in terms of distance between the tip and the sample, and also flow rate, speed, and pressure. And here you can see some pictures of the first samples that we used at the beginning. We see that when we increase the number of passes, we start to see one film that is a little bit more homogeneous. So this was at the very beginning, the first trials that we did require optimization. Here, this is one SEM image of one atomic force microscope tip. We tried to coat it with the graphene oxide, but we failed. As you can see here, it is not a conformal coating. After practicing a little bit, we achieved some conformal coating of the cantilever, which is a flat and long surface. It is an easier surface to coat, but at the end, we managed to coat perfectly a very complex, irregular shapes like the pyramidal tip of an AFM. In fact, in our study, what we have used are solid platinum AFM tips. This is important because metal-coated silicon tips can degrade after some electrical measurements. These solid platinum tips cannot be degraded. And then we use the spray coater to put the graphene oxide on this tip. Okay, so you can see we have used two setups. The first one is we use the tips that are coated with the graphene oxide, but we also use some as received tips, and we put the graphene oxide on the surface of the sample. So using this setup, this setup here, of course, the tip is sharper, so the apex is the radius of the tip at the apex is much smaller, and here it is a little bit higher. We have also calculated the effective contact area between the tip and the sample using the Hertz model, and we have observed that here the contact area is 8 nanometers square, and here is 50 nanometers square. And then here there is the really good innovation of this project, which is we have used a standard conductive atomic force microscope to measure electrical properties of these material systems. In a standard atomic force microscope, normally you can apply only up to 10 volts and measure currents up to some nanoamps. There is no current limitation, and you can only apply ramp voltage stresses. This is quite limited, to be honest, if you want to measure synaptic response. So what we have done is to use a semiconductor parameter analyzer connected between the tip and the controlling computer. And what we see in this case is that we can apply much higher voltages if necessary. We can measure a very wide current dynamic range. We can apply current limitation, and we can apply both ramp voltage stresses and pulse voltage stresses. So here you can see one example. This is one measurement done with the standard setup. We can apply a ramp voltage stress. We observe that the current increases sharply, and then we observe that it decreases in the same cycle. For the next cycle, I go here again, and I see again the relaxation. So we are observing quite good threshold type resistive switching, which is something necessary to fabricate a neuron, an electronic neuron. We analyze the variability of the set and preset voltage and see that it is reasonably small with no match between both voltages, which is something quite good. In the next step, we try to do the potentiation of this material system using the semiconductor parameter analyzer and the pulse voltage stress tool. When the time between the pulses that we apply is large, we observe that it can this conductivity increase that we have induced during the pulse, it can relax. And if we start to decrease the time between the pulses, this relaxation, this time is not enough to relax all the modifications in the atomic structure of the material system. And then if the time is too small, not only cannot relax, but then we see a erratic increase of the conductance. This is what we will call the potentiation. By tuning the electrical stresses, we have managed to achieve a very smooth and progressive potentiation of the currents across this material system. And we can observe for this is different sites we can observe that the variability of the currents is reasonably low, as you can see in this plot. This is the current that we measure versus pulse. I have to emphasize that this is right current, not read current, because the measurement is done when we apply the pulse that induces the conductance change, so it's the writing. And this right current is as low as 1 microamp and even below 1 microamp. We have observed that when we compare with many other studies in the literature, we have observed that this value is remarkably low, which is also probably related to the fact that we have a very small cell, because our work shows the smallest cell possible. Here, we didn't include the STM work because it has this nano gap that is not suitable for, it doesn't match real devices. So you can find more information about these references in our article if you are interested. We can also apply a little bit higher voltage for the pulse, and what we observe is that this synapse will potentiate faster. You see, in some pulses we already arrived to this level. So actually, this is also showing that the speed of the potentiation is strictly related to the height of the pulse, which is something that needs to be present in when this device is used in a real system. In the next step, we measure excitatory postsynaptic currents, which is basically the transmission of electrical spikes or action potentials from the presynaptic electrode, which is the platinum electrode in our system, to the postsynaptic neuron, which is copper. Actually, here, I'm sorry, this should be copper. So here we observe 4 trains of pulses, and the voltage of the pulses is increasing in each train. And what we observe is that this signal is starting to transmit successfully to the postsynaptic neuron. We observe something interesting, which is between the last pulse here and the next one, there is a relaxation, which is also confirming the presence of this threshold region. So in the next step, we try to apply a little bit higher pulses. And what we observe is that we can start to increase the current across this system nearly linearly, again, as shown in the previous example. We can also see the depression. But if we apply higher stresses, and especially if we apply them to the copper electrode, not to the platinum electrode, what we observe is that we can increase the conductance above the level of the quantum conductance. This is important because now what we observe is that this resistive switching behavior is non-volatile. We can achieve this set behavior, and now we can only reduce the conductance by applying another stress with the opposite polarity. All these currents are producing this bipolar resistive switching now. And we also analyze the variability of the currents and of the set and reset voltage, and we observe that they are not overlapping, which is something what we needed also for our study. So in the next step, we analyze the resistive switching mechanism. We have done computational calculations to calculate the temperature that is being produced in the conductive nanofilament when we apply the electrical stresses to the copper electrode. And what we observe is that the non-volatile regime is only achieved when the temperature of the filament increases remarkably above hundreds of degrees. Actually, this is something that it is very important because it shows that it is a thermally activated behavior. So in summary, we have concluded regarding the resistive switching mechanism that we have 2 types of switching. When we apply a positive stress to the platinum electrode, the platinum is a noble metal and it has a very low diffusivity. And therefore, the conductance change in this material system is normally produced by the migration of oxygen atoms, which produces some oxygen vacancies. When we apply the positive bias here, copper electrons don't enter because copper ions are positive and they will move in the opposite polarity. So this is what leads to the volatile resistive switching regime. And for the non-volatile regime, this only happens when we apply the negative polarity to the platinum electrode. In this case, the platinum is still a novel material, so it cannot enter in the graphene oxide film. However, now the positive copper ions can enter, and this is what produces this non-volatile regime, because these copper ions will stay here unless we apply a negative polarity in order to reverse polarity in order to move them away. So in conclusion, when studying electronic devices for neuromorphic computing, we need to use very, very small device size. In our study, we have employed one conductive atomic force microscope, and we have coated the AFM tips with graphene oxide using a spray coater. We observed that for the platinum graphene oxide copper synapses, if we can observe threshold type resistive switching with linear potentiation and ultra low right currents when we apply the stress at the platinum side. When we apply the stress at the copper side, we can observe non-volatile bipolar resistive switching, which is related to the formation of a filament. We also can conclude that the resistive switching is related to the migration of oxygen when it is when the stress is applied at the platinum side, which is threshold type resistive switching, and when we apply the stress at the copper side, the resistive switching, which is non-volatile, is produced by the migration of both oxygen and copper. And finally, the resistive switching in the non-volatile regime is a thermally activated phenomenon. So that is all for my presentation. Thank you very much for your attention.